Hello everyone and welcome back to another video. Today we'll be taking a look at another British Informatics Olympiad question, and we'll be taking a look at a very nice question taken from the 2013 paper. So it will be a question 2, so as always there's an issue of understanding the actual question. So to make it easier, I've highlighted some of the key parts of the question, but I'll let you have a quick read of the question. Feel free to pause the video before I then explain what the solution is through the code. Okay, so that's pretty much it. Now let's have a look at the actual code. So with these questions, it's essential to create some sort of class. Now, what this allows is for all the methods to be like kind of self methods, and the reason for this is it allows great reusability, and it just makes the code much cleaner and shorter, and therefore easier to understand, easier to work with. So yeah, now let's have a look at the initialize method. So we initialize the 5x5 grid for the Neutron and all the 5 pieces of each player, and we initialize the rows, all of the players, all of the counters for player 1 on the top row and player 2 on the bottom row. And we also have this locations dictionary. So this basically keeps track of where each of the counters are for the players, and this will come in great use for the future, since remember we have a specific order in which we have to move the pieces. So that's that, and we also update the locations with these tuples, and we initialize the neutron to having a value of 25. And now the reason for this is because all the other counters have been given a numerical value. So player 1's 1, 2, 3, 4, 5. Player 2's are 10, 11, 12, 13, 14. No, sorry, 11, 12, 13, 14, 15. And the neutron's been given 25 as a value. And what we do is we have the orders for each of the 2 players as input, and then we have the directions. So all of these are basically unit vectors in each of the directions. So for example, for the one which goes up, it would be -1, 0, then -1, 1, 0, 1, 1, 1, etc., etc. And now this will come very handy in the future when we need to decide which direction to move the neutron in order to win, for example. Which is why we have these unit vectors in each of the possible directions. So now we go on to the move function. So what this does, it's quite self-explanatory, since as the problem statement said, for a specific piece or a neutron, we have to move it in that particular direction as long as it possibly can, basically. So what we do is, for a specific RC value, we move it, while the condition is true, we continue moving it in this direction. But before we do that, we need to initialize the initial position of that particular piece to being 0, since that piece is basically getting picked up and moved onto another piece. And now we have this while loop. So what this does is, first of all, it checks whether the element, it checks whether the initial element is blank, and then what it does is it checks if that particular element is also within range. Now the reason we're checking whether it's blank is because you can't append onto an element which it already has a piece onto it, right? And these two basically check whether the row values are within the limits. And then one more thing which we have to check is we not only have to check whether the specific row values are in the limits, but we also need to check whether applying the particular direction vector to that particular row and column value, whether that will also be in the limit, okay? Since, for example, if we're on the very edge and then our direction vector takes the piece off the board, then that obviously is impractical. So we need to check for all 5 of these conditions. Now, unless all of these are met, we will not proceed. So if they're not all met, then we'll basically break. But if they're all met, then we have further conditions to check, is whether the new direction vector applied to the particular column value, row and column values, if that particular value is empty. If that's empty, then we can finally update our row and column value, and then we basically just break if these two conditions are not met. And then we repeat this code indefinitely until we reach the end of the grid, or we reach a particular place where we cannot move the piece any further in that direction. And then once we're done with this, then we basically just set that particular row and column value of the grid to being the piece which we are moving. And then we also, very importantly, have to update the locations array of this piece to its new row and column value. So that's the move function, which is over there. And now we will go on to the will win. So this is 60 lines long. It is quite long, but let's quickly have a look at it. Now, if you notice, we basically just had to duplicate this code, since we need to decide whether the first player will win or the second player will win. And unfortunately, we cannot reuse this particular code for the two-player values, since each of the values have a different requirement. So, which is why it looks like much longer and more complicated than it actually might be. So, but either way, let's dissect what this code means line by line. So we initially have to determine what the row and column value of the neutron is. And then we basically just set the particular, if the player is 2, then the other player is 1. If the other player is 2, then the other player is 1. And then we initialize our A array to being a certain array for each of the 2 players. And then the other is also initialized to an empty array. All of these, the meaning of all of these will become clearer as we walk through the code. So we iterate through all possible directions, and then we basically get a row column value of the particular neutron, and we set that to equal to our row and col. And now what we do is pretty much exactly how we did in the move function. We continue operating in that direction until we reach the end. And now, if the particular row value is 0 or the row value is 4, then we basically know that we've reached the either the top row or the bottom row, which constitutes a win for either player 1 or player 2. So which is why we then append it to the A array for the corresponding player. And now, if the row value is 0, then we append it to player 2. If its row value is 4, then we append it to player 1. Otherwise, we append it to other. So now the reason why we have this other function is because if you recall inside the question, what we had is we had some sort of rule engine to deciding the moves. So if the player is able to win with moving the neutron, then you have to play that move. But then if the player is forced to lose, basically, you need to play the first possible move, which can result in that loss. So which is why we need to have this other array. What this does is it basically keeps track of any other moves which we can make, which don't automatically end the game. So this is very important in deciding for this second particular decision-making criteria. And now, which is why we append the corresponding arrays. And now we repeat this for each possible direction within the 9 directions. And all of these 9 directions have their corresponding vectors inside the initialize function. Okay? And now what we do is if the length of the player is greater than 0, that means that the player has a particular win condition. Then we return that particular direction vector as well as true. So what true does is true means the game has indeed ended. Otherwise, if the length of the other player is 8, which means wherever the current player moves their neutron, the other player will win. So then we also return true since the game is ended, and then we return the first particular element of the particular direction vectors of the other player. Okay. And now else, this is where most of the conditions will fall in, is where we don't end the game inside this move. So then else we need to decide what the move which we perform will be. And now if we just go back to the question and remind ourselves what that will be, the question says that if the first two conditions are not met, then the player needs to move the chosen piece, move the neutron in a direction such that it frees up the chosen piece. Okay, so now let's have a look at how we have implemented this. So what we basically do is again, we repeat this particular block of code. We just check whether the particular direction vector is valid. And then what we do is, if moving the neutron in that particular direction, so which is why we move in all 9 directions, if moving in that direction will result in a valid configuration. And now the way we determine whether it's valid is if it's directly next to the particular neutron. So then, the particular piece which we need to move. If the particular piece is completely trapped with other pieces, then we basically valid will be set to false if there's even one opening for that particular piece. Otherwise, valid is true. And then what we do is, if valid is true, then we have to move the neutron out of that particular place, just so it frees up a particular direction for the current piece which we need to move. And then we return direction, and here we return false. The reason why we return false in both of these cases is because the game is not ended. The game is only ended if these first 2 conditions have been met. And now, if it doesn't enter any of these if blocks, then what we basically do is we return direction vector 1 and then false. So now the reason for this is because if there's no direction inside this which the conditions are met, if it breaks out of it every time, then we just return it through the first particular direction by default. Okay, so that was the will win function. Now, if you understood this, good job. You're literally like 95% of the way there to executing or solving this problem, I guess. But now let's have a look at some of the other functions. Okay, so now let's scroll down a bit. Now we just have this play function, which basically just incorporates everything which we have in the will win function and the move function into one. So we initialize this done variable to false. So what this done it keeps track of is whether there are still moves which are yet to be played inside the game. And while the game is not done, we will basically just iterate through each of the possible 5 positions of each of the players. And then what we do is, if the player is 2, then we have their particular chosen values updated in the self.locations. And then if the player is 1, we do the opposite. And then what we do is we have the direction and done of the will win. So will win, it basically just, it says will win, but it will choose which direction you should move the neutron and the piece. And then it'll update those corresponding values as well of the neutron. Okay, and now if done, it will also move. And then if done, that means that the game is basically finished. Then we return out of this play function since we're basically finished. And then what we do is we also, for each of the directions and coordinates, we need to actually move in that particular direction. Since we need to move the neutron in that particular direction. Okay? And now if I equals 0, then we'll basically output. And now what this means is that if we're onto the if we're onto the 0th particular position within our criteria of selecting which counter to move, then we'll basically output since that's what the problem statement requires. Okay, and now what we do is we iterate through each of the 25 cells, and then we print either dot, f, or star as required, and then we basically just need to also print end, a space at the end, and then just print the line. All of this is just kind of like admin work, if you like. We just need to make sure that it outputs in the correct format. And then these are quite self-explanatory. We just take the inputs of the preference lists and then pass them as input to the game class, and then finally play the game and then output. So now let's have a look at if this mammoth code actually works. Let's go back to the question and get some of their test data. So it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. We basically have this particular output. If we go back and compare, we can see that this is indeed correct. Let's just compare with the final one. Nice. So our code does indeed actually work, which is quite nice to see. So that's pretty much it for this particular video. I really hope you enjoyed watching the video. Hopefully you learned something new about how we tackle these question 2s, since they are quite challenged to implement. And if you did, please be sure to leave a like and subscribe. Hopefully you find this video useful. Please do check out my GitHub as well if you would like to play around with this code in more depth. Thank you very much for watching. I'd like to see you in another video next time. Thanks. Bye.